In the previous video, we were talking about the DBpedia entry for Berlin, so let's continue to use Berlin for this example and actually look at the DBpedia entry for Berlin. Now, we could be looking at the DBpedia entry for anything, really, but Berlin makes a nice example. I've been to Berlin, I liked it a lot, and I'm sure it makes a good example about lots of things, so let's just go with that. So this is the entry for Berlin in DBpedia. And all of these entries are quite long, and we're certainly not going to look at every entity value pair here, but let's just kind of browse through it a little bit. So first thing to notice is that it is an entity of the type city. And it says from the named graph dbpedia.org. Right? It is a named graph. It is a labeled graph because, as I said in the previous video, all of the edges and nodes have labels on them. They're all entities and named relationships between those entities. So the first thing we have is the abstract in a whole bunch of languages, all of which are pulled from different language versions of Wikipedia. And the entity abstract is declared in OWL, which is an acronym which stands for Web Ontology Language. And yes, I know that the W and the O are reversed there. What can I tell you? It's an acronym that isn't really an acronym. So the Web Ontology Language, OWL, is implemented in XML using the RDF model of triples that we've been talking about. So, for example, Berlin has the area code 030, right? You have entity Berlin, entity 030, relationship area code. Berlin has the population, approximately 3.5 million. Entity Berlin, entity 3.5 million, relationship population. So DBpedia, and because it's relying on the web ontology language, is building up this network of RDF triples. Now, one of these triples is country. There is a relationship being established here between Berlin and the DBpedia entity for Germany. Berlin and Germany are two entities. The relationship is country. So let's actually look at the declaration of the relationship country. So the first thing to notice is that it's declared in RDF and RDFS, and that it is also an entity declared in DBpedia. So as I said, there are lots of triples being declared here. For example, we have the leader and the leader's title, governing mayor. And we have population. And we have population, it kind of got buried under my previous line here, population as of. We could go through each one of these triples in turn, but the point is each of these triples has a different value. For example, the name of the governing mayor is a name, which can be controlled by a name authority file. You can have a controlled vocabulary that is a name authority file, similar to the Library of Congress name authority file, although, of course, that isn't going to cover probably mayors of German towns, but the point is it's a controlled vocabulary of names. You have population, which is a number. You have population as of, which is a date. So that might be encoded in ISO 8601, which of course we've looked at many times already. So you can have encoding schemes for how entities are declared. Let's take a look at the DBpedia entry for the entity leader. Now, again, it's declared in RDF and RDFS, and the range, that is to say, the way in which this entity is constructed, is that it is a instance of the DBpedia entity person, right? Leader is a subtype of person. Now let's take a look at the entry for population. And what we have here is that the range is that population is a non-negative integer. Population is declared as a non-negative integer. It is an instance of that class of things in the universe called non-negative integers. So we have lots of ways in which the value of an entity can be declared. You can have a block of text like the abstract. You can have a number like population, and even a subtype of the class number, a non-negative integer, because having a negative population wouldn't make any sense. You can have a date encoded in, say, ISO 8601. You can have a controlled vocabulary of names. You can have things that are instances of other classes, like leader is a subclass of person, for example. And we even have some use of Dublin Core here. We have the DC terms subject, and Berlin has all of the following subjects, or to say that differently, Berlin is an instance of all of these different subjects, capitals in Europe, city-states, European capitals, etc., etc. So there are all of these entities that are categories, and Berlin has a relationship with all of them by being a subtype of all of those categories. Again, DBpedia is declared mostly in OWL, the web ontology language, and we have the OWL same as field element and a whole set of values for things that this DBpedia entry is the same as according to OWL. And mostly, as you can see, these are different declarations of Berlin in different language versions of DBpedia. And down at the bottom here we have something that isn't DBpedia, it's Psych, which is a project to build a massive ontology of common sense knowledge. The point is we have all of these different graphs declared in OWL in different languages and even different projects that this entity, this entry for Berlin says all of these things are the same. And therefore, if you're linking up graphs, you can say this entity is the same as this entity because it says so in the declaration for this entity. So suddenly you can merge two graphs into one because what looks like two distinct entities really are the same. Similarly, you have something like birthplace of, and this very extensive list of people who were born in Berlin. And so now we're able to start merging graphs that are about different entities. Here we have this graph about Berlin. It has relationships with country Germany, with population numbers, etc. And oh, by the way, there are these other graphs over here about all of these people, and you can connect those up because this person has a relationship with Berlin. The entity such and such a person has a relationship with the entity Berlin because the labeled edge there would be labeled birthplace of. And so you can see, I think, how you can start to merge graphs of Berlin with graphs about other entities. And I think you can pretty easily see how you can expand on that and start building up a very large network of entities and relationships, build a graph containing data about lots of entities.